All right. So this should be recording and it should be nice and fun. Let me show you guys a couple of things before we dive in, just because they're really helpful to know. Um, so if you go to tinyurl.com/Gabe Tutoring, so who I am and what I do, this will bring you to a Google Drive. And in it, you'll go to second year stuff because you guys are in sophomore year. Then I recommend that you probably go to BU Orgo. I don't have a folder in for Northeastern just yet, but um, as we generate more and more stuff between us, I'll be able to have more. But if you go in there, it has lots of good resources, different things to be able to, um, like, oh, I'm struggling with NMR. How can I do NMR? Or, oh, I don't really understand acid base again. I wish I could get more information. Or, oh, how do I do functional group stuff? And all these notes were generated by Dr. Rubio, who was fantastic at teaching this information. Um, Also, in these folders are like different practice things, so you can practice. They're pretty difficult. So if you're able to do these, then you are pretty much all set. And then these are the exams as well and stuff like that. Just so you're aware. And then as well, if you go to tinyurl.com/Gabe Tutoring YT for YouTube, this will take you to the YouTube channel that just has all the stuff in it that you'll be able to view and everything. So it'll be, and this video will go up on the YouTube channel for you.
And may we subscribe to that?
Oh yeah, feel free, do whatever you want. Um, I don't, I'm not going to monitor it. I'm just going to be a way for me to put things up. So the so that will, if you have questions, anything like that, just put them in the group chat. It's a much better way of like getting me to respond. Um,
Hello.
Hello. Uh, Sweet. So without further ado, let's get started with this. Um, all right. Are you guys able to see this screen, this black screen?
Yeah.
And can you see me drawing on it?
Mm-hmm.
Sweet. All right. So I believe what we are talking about today is acid-base chemistry. And acid-base chemistry is a pretty important part of organic chemistry because it is one of the fastest portions um, of what am I trying to say? It's fast, it's everywhere, and it's always in your face. And whenever we talk about um, kind of chemistry in general, you can pretty much bring it all the way back to acid and base, and you'll be like, oh my god, this is where this reaction is coming from, and pretty much the basis is what we're talking about. So we're talking about acid and base chemistry. You guys can see this writing, right?
Yeah.
I want to make sure. Whoops. There we go. Now, you guys might remember in Gen Chem that you had a few different definitions of acids and bases, right? You talked about Arrhenius acids, maybe you talked about Lewis acids, but primarily in organic chemistry, we're going to be talking about Bronsted-Lowry. Bronsted-Lowry acids and bases. Does that name sound familiar at all?
Yeah.
A little bit, yeah. So the big part about Bronsted and Lowry their idea is that you have this conjugate pair going on, that you have an acid and a base, and by reacting them together, we end up with an acid and a base. However, the nature of those two structures changes. Put that in brackets, and then that brackets. Sweet. Now, before we go any further, I have to mention this because this is the thing that everybody always ends up forgetting. And if you show me your exam or a problem or something like this, and you don't remember this fact, I will kick you in the shin. That acids donate. All right. What do acids donate? They donate protons or hydrogens or positive charges, you could say, but acids donate. So what do? They donate. And what do bases do? Bases accept protons or they accept hydrogens. Whichever way you want to say it, they mean the same thing. So once again, what do acids do? They donate. And what do bases do? They accept. If you try to tell me otherwise, like some of the Harvard kids do, I will yell at you and then kick you out. This isn't even like an interpretation issue. This is just a definition issue. Cool. So with that in mind, what we can do is we can go to the Bronsted-Lowry kind of setup. And what we can say is that this structure over here can kind of reach out a hand and grab this hydrogen. And we can see that in the resultant, that we can see that this B molecule ends up having this hydrogen attached to it. Let me draw it a little bit closer. And it results in this HB complex. Likewise, this A molecule gives up the hydrogen and becomes this a negative complex. And so the question is, did this A molecule here, did that donate a hydrogen to the B molecule?
Yes.
Totally. It gave it up. It got rid of the proton, right? So if you get rid of a proton, if you donate it away, if you get rid of it, you are an acid. Likewise, we could use that same sort of analogy to come out, or same sort of definition is for this B molecule. It accepted this proton from the acid, and so we know that this is the base. Likewise, we can go over to the other pair and we can say that there's no reason why this A molecule can't take this hydrogen right back. Boom. Maybe it's weaker, maybe it's not really favored for it to happen, but it's definitely possible. And so this A minus is accepting a hydrogen, right? So if it's accepting, it is now a base, except we call it the conjugate base. Likewise, this HB complex is donating the hydrogen to the A minus, and so this is the conjugate acid. This should all pretty much be review from Gen Chem, right? No, nothing new, anything like that. The other big thing I'd like to point out is how do we get these charges? So what's important to know is that this acid is currently neutral, and it's losing the positive charge in the form of the hydrogen. Also, am I recording still? Yeah. And so 0 minus positive 1 equals negative 1, which is how we get that negative charge. And then likewise, we have this base is neutral and it's gaining that positive charge, and now it's positive 1, which is how we got that charge. So you can always use this math-based charge analogy in order to figure out, oh, I don't know if it's going to be charged or not, be able to figure it out. Cool. This is kind of the very, very general part. This is pretty much all you really should know from Gen Chem. And if you're able to kind of remember this Bronsted-Lowry stuff, you're in great shape for this lesson. Moving on from that, the The next part that usually comes from Gen Chem that people always ask me about is they're like, well, what about Ka? And then all of a sudden we start talking about in organic chem, we start talking about pKa. And so the question is, what the fuck is this? Because that's what they always ask. And so the answer to that question is that A is the acidity constant. And it's constant with a K because it's German. Likewise, well, what does that really mean? Like, yeah, it's the acidity constant, but what is it really saying? Is it saying it's the dissociation constant? Oh, dissociation. Dissociation is like donating. So what this is essentially saying is that we're taking an acid and we are donating away or dissociating into the proton in the conjugate base. Because remember, if you dissociate, then you're an acid. Because now you have allowed for this H plus to be free to be able to be donated somewhere else. So this is just another way of writing all the same sort of information. Does this kind of sort of make sense so far? But this doesn't really answer our question about what the fuck Ka is. Well, what I'm going to tell you is that Ka is just the numerical way of determining the strength of an acid. That's all it is. It's just a way for us to be able to say, okay, this thing is fundamentally numerically stronger than this thing. Someone give me their favorite acid to work with in the chem lab.
HCl.
HCl, great, perfect one. The Ka of HCl is equal to 10,000. So, 10,000 is a number, whatever that really means. And then another acid that we could totally work with is something like acetic acid, which is vinegar. Very, very, very common acid, except it has a pKa, or sorry, it has a Ka of 10 to the negative 7th, which is 0.0000001. And I'll let you guys catch up because I know I'm throwing like a whole bunch of stuff down. By the way, if I ever go too fast or you want me to repeat something, let me know. I'm happy to do it. I also repeat myself constantly, so generally people don't really need me to do it. But if usually it's slow down, that's the big thing. So these are the strengths of the two acids, right? And what's important to know is that we can see that based on these two strengths, that HCl is stronger. How much stronger? It's 10 quadrillion times stronger. So this is what Mother Nature is telling us, that if you use HCl and acetic acid at the same time and you put them in a beaker, hydrochloric acid is going to be 10 quadrillion times stronger. But the thing is that if I want to graph this, how could I make a scale that goes from 10,000 to 1 millionth, right? There's no way of creating a scale that'll make that happen, right? Likewise, I've never really looked at something and been like, oh yeah, that's 10,000. I've never been able to like logically, like I can't imagine that number. Same thing, I can't imagine 1 millionth. I've never looked at something and been like, oh yeah, there it goes, a millionth of a thing. So Ka isn't really helpful. So what we're going to do is we're going to use the function P. And P is equal to the negative log. And by using the function p, we're going to take the pKa, which is the same thing as saying the negative log of 10,000, and we get -5. Same thing, if we take the pKa of acetic acid, convert this over, we get 7. Oh, okay. Now I can rationalize 7, 7 and 5. I can put 7 and -5 on a graph. That's perfectly fine. All that pKa is just a fixed scale Ka. That's all it is. There's no difference between what these two things are measuring, except now I can rationalize and put it on a graph easier. Does that make sense? So is it still measuring the numerical way of measuring the strength? Yeah, totally. Is hydrochloric acid still 10 quadrillion times stronger? Totally. But now I can put it on a graph, and now I can describe these things in much simpler terms. Does this make sense? So this is like the big part of acid and base chemistry, is that we're not going to be talking about Ka of anything. Ka is too large to really determine anything. However, we can talk about pKa. And so what's important to know is that every step, so going from like 2 to 3 or 3 to 4 in pKa, is times 10 the strength. So going from 2 to 3 is really 10 times the strength. And the reason is because we're talking about a log scale, right? So likewise, if you're going from 2 to 4, we're talking about 100 times stronger. So I don't ever want to hear, when we're talking about pKs, I don't ever want to hear, oh, it's twice as strong. No, it's at least 10 times as strong. All right, so we're always talking about multiples of 10, especially when we start going up and up the log scale. Does this make sense? Sweet.
Yep.
Likewise, what I want you to notice too is that pKa, the stronger the acid, the more negative the number. So smaller or negative pKa's equal stronger acids. And once again, that has to do with the fact that we're talking about a negative log. A negative log will always shift things towards the negative end. Sweet. So with that in mind, this is pretty much all the definitions that we're really going to be talking about in acid and base chemistry. We're going to be talking about the fact that we have two sides of the equilibrium equation. Acids donate, bases accept, and that pKa is just a way of measuring the strength of an acid. That's all it is. And with that in mind, we can finally dive into, well, how do we actually do acid and base problems, right? How do we actually make these things happen? And I need to pull up my reference. Whoops. All right. So what I'm going to tell you is that I'm not exactly sure what your exams are going to look like, but if I imagine they're anything like the other 5 schools that I've tutored at, well, I've tutored at Northeastern before, but not for your teachers. I imagine it's going to look something like this. You're going to be given 2 structures, an equilibrium arrow, and then 2 blank spots. And essentially, all you're trying to do is we're trying to fill out the information about, what is HA, what's B, what's the acid, what's the base, what's the conjugate acid, and what's the conjugate base. So that's essentially all we're really trying to do. And you're probably going, are your exams online?
I
Sure.
believe so.
Yeah,
Yeah.
Yeah, they're online.
the so what will probably be is that you won't have to draw the structures. It will be more like select multiple choice, or you know select the choice that shows the correct structures, or select all that applies, something like that, which isn't great, but it might end up being a little bit easier, in fact. So with that in mind, the last part is then determining, well, which side of the equilibrium arrow is favored. And I'll show you a way of doing that. And essentially, usually they either have you circle it, or it'll be like, oh, towards the left, towards the reactants, or something like that. But that's essentially what it is. So approaching these kinds of acid and base problems, I want you to do 3 steps. I want you to determine who is the acid, the base, the conjugate acid, and the conjugate base. Number 2, I want us to assign the correct pKa values. And then finally, we're going to determine the equilibrium, which just means that we're going to choose the arrow. Sweet. So let's say that you're given this molecule. Probably will end up looking something like this. And let's say that you're given the pKa of this structure is 4, and then the pKa of this thing is 35. So this is all you're given. This is a really common setup for these molecules, or for these reaction types. And basically this is all it is, and then they just say solve. For ease, I just want to give these things some names so that way we're all talking about the same thing. So I don't know. We'll call this one Dave. And we'll call this one, I don't know, something like Nancy. So we have Dave and Nancy, and we're going to react them together, and we're going to see what happens. So the first step is we have to determine who's the acid and who's the base. Okay? So is your professor's going to have you memorize pKa values?
No.
Are you going to be given a pKa table?
I think she talked about something like we have to determine, like, by looking at the structure, like we have to see which one's like more acidic and less.
Makes sense. So she's going for a purist view of chemistry, which is totally fine. My cheat sheet that I'm going to give you a list of pKa values that are always just really good to know. You're going to need to know them for the rest of the course anyways. I'll give you a list at the end that you can start putting into like a Quizlet or something like that. But the one trick that I'm going to give you right now is that nitrogen is always a base. Oop, this shouldn't be. This isn't 35. My bad. This should be 17. Me trying to be too clever. Nitrogen is always a base unless it has a positive charge. That's my little cheat sheet. And the reason for that, in case if you're interested, is that nitrogen has that lone pair, and it's just for the way that it works out with the electronegativity and that lone pair, it's just really, really, really hungry to always steal protons if they're available. So when in doubt, if you have a nitrogen on its own, it's probably going to be taking hydrogens, which we'll see in semester 2 is a big, big problem of nitrogen because it's also just a really nasty chemical that will kill you. So don't drink nitrogen-containing compounds. They also don't smell good. Cool. So with that in mind, from here right now, let's talk about a couple of different things that we can notice. First of all, I noticed that we have a functional group right here. And this functional group, as you may know, is a carboxylic acid. Likewise, I can look at this functional group right here, and I can say this is a primary amine. And based on those, I'll give you that cheat sheet. You'll be able to identify these functional groups and then be able to determine what the pKa should be. So as of right now, which one are we taking a guess is probably most likely the base?
Amine.
Definitely the amine, right? Nitrogen is always a base unless if it's positively charged. So it's a good guess to say that this is probably the base. Are there a few exceptions when it's not? Yep, and we can talk about those as well. But for the most part, nitrogen will always act as a base unless if it has a positive charge. So if Nancy is the base, then that means Dave has to be the acid. No ifs, ands, or buts, right? Because we're talking about Bronsted-Lowry setup, and we know they have to be conjugates, or they have to be pairings. Likewise, what we can do is we can fill in on the other side that the conjugate of Dave, will be the conjugate base, and then we have the conjugate acid over here as well. So just by being able to identify one portion, we're able to figure out the rest of them because they're all opposites of each other. From here, what we know is that here's the nitrogen, and the nitrogen is most likely going to come and take this proton, right? A carboxylic acid. So it's carboxylic acids are one of the more acidic functional groups that are out there. So it makes sense that this molecule is going to reach out and grab this hydrogen. And so now that we've kind of identified where the transfer is going, what we can do is we can just redraw these structures exactly the way that we found them. Pausing just to check the charges. Now, you could write it could be written as two different ways. Especially if you guys have a written component, it could be written as two different ways. Both of these show the same thing, that this conjugate acid has either 3 hydrogens just written together, or that it has 2 hydrogens that it originally had, and we're just purposefully showing the third one that got picked up. They both mean the same thing. They're both completely accurate. neither one is more accurate than the other. However, if you tutor with me, I always try to keep things condensed as much as possible. So you won't really see me doing this. However, just know that that is a very valid way of writing it. And then what we can do is we can do the math to be able to determine what the charges will be. So we knew that this carboxylic acid was originally neutral. It's losing a proton, so now it's -1. And then same thing with the nitrogen. It was originally neutral, and it's gaining a positive charge, so now it's +1. And let's double check that that makes sense. We said that nitrogen is always a base unless if it's positive. So does this nitrogen have a positive charge? Yes, it does. Well, we have to make sure that it's labeled as an acid, and oh look, it is. So it's another way of just double checking that we've done everything correctly, that we have this kind of guess and check going on. Now we have to go to step 2. We're going to assign the correct pKa values. And what I mean by that is that we're talking about pKa. So we're talking about the acidity constant. So we can't leave pKa's assigned to basic structures. So let's take a look at Nancy, for example. And Nancy, I've labeled with pKa of 17, right? But Nancy is a base. So can I describe Nancy with a pKa? No, it makes absolutely no sense to describe Nancy like that. So what I have to do is I have to take this pKa and move it over. I have to move it to the structure that is actually an acid, because I cannot describe basic structures with a pKa. Does that make sense? Good? Cool. This is a really huge component of acid and base structure or reactions, because this is something that people fail to do a lot of the times, and then they like, I don't know how to do this problem. You have to make sure that you're assigning pKa values to the acid structures. This also comes back to the fact that the list that I'm going to give you shows the most common functional groups that are going to be acting as acids, okay? So it's all about just understanding of what's going on. The other big thing to know is this structure over here on the conjugate acid. Is this a primary amine still?
No.
No, this is now an ammonium. Likewise, is this thing still a carboxylic acid? No, it's now a carboxylate. So the big thing to know is that when you are memorizing these, the other thing you could say here is ammonium or protonated amine. Oops, that shouldn't be a slash. Protonated amine. Either one of those is fine. So the big thing to know is that you have to make sure that you're picking the pKa value for the structure that is acidic, because I'm going to give you the pKa of amines, but if you choose that over here, it would be wrong, because the pKa of a protonated amine is not the same thing as a regular amine. So once again, you just have to be checking to make sure that you have the correct structure and that you're assigning the pKa values correctly. As of for this lesson, I'll just give them to you so that way I don't hand you like a giant list, because God, that's awful. Cool. So we have finished the second part, and now we're on to the third part. And so the third part can kind of be done one of two ways. The first way for determining the equilibrium is to logically think about it, or theoretically think about it. And so what I'm going to tell you is that Mother Nature, the big MN herself, will always, always, always favor the weaker acid. And what's the reason for that? Is because if you have, if you have a screaming kid and you have a really quiet kid who's playing in the corner, and the screaming kid is like kicking you in the shin and being really annoying, who are you going to throw out the window? I'm going to get rid of the screaming kid, right? Because they're annoying and I don't like them. Same thing with Mother Nature. Mother Nature will get rid of the stronger acid because it's more reactive and it's more unstable. So by contrast, we could say that the weaker acid is more stable and less reactive. So it's not going to rip things apart and kill babies. It's just going to sit there and it's going to be fine. And so we're going to choose the arrow that's facing the weaker acid. And for this problem, is that going to be towards the products or towards the reactants?
Products.
Products.
Towards the products, right? How do I know? Well, I compare the two acids. We have 17 and 4. The bigger number is the stronger acid, so I'm going to choose, the bigger number is the weaker acid, so I'm going to choose 17. Sweet. The second way is to think about it mathematically. And this is probably the KEQ equation that he gave you in class or you found in the book or something like that. And essentially what it is that KEQ, the equilibrium constant, is equal to the product pKa minus the reactant pKa. So in this case, we're talking about 17 minus 4, which is equal to 10 to the 13th, or 1 with 13 zeros following it. And so what KEQ says is that if KEQ is greater than 1, then we're going to choose the reactant side. Sorry, choose the product side. But if KEQ is less than 1, we're going to choose the reactant side. So based on that number, we know that 10 to the 13th is 10 with a lot of zeros following it, which means that is this thing bigger than 1? Yes, it is. So we're going to choose the product side. I highly, highly recommend checking your logic with your math or checking your math with your logic. Don't rely on one method or the other to be able to tell you which one is the correct way of doing it. Both of them together bring you to the right answer. How do we feel about this? Good? Kind of makes sense, a little bit less complicated than maybe what class was like, hopefully.
So I just had a quick question.
Sure.
So like on the reactant side, like with Nancy, since it's a base, so would it not have a pKa at all?
Correct. We cannot
Okay.
describe, that's not true. It could have a pKa, but the pKa would not describe the conjugate acid. The pKa would have to describe the base. So we
Okay.
could say that it's the pKa of the amine, but the amine is not acting as an acid in this case.
Okay.
So all hydrogens have pKas, but we only care about pKas of the acid structures, is the way I guess I want to say it.
Okay.
Sweet. Do we want to do another one? Another practice? I think that's probably for the best. What's someone's favorite flavor? Give me a flavor.
Coffee.
Ooh, coffee. Do you want the bitter coffee molecule or do you want the coffee flavor molecule?
Let's go with the coffee flavor.
Coffee flavor it is. I used to know this one off the top of my head and now I can't remember it. All right, I'm going to modify it just slightly because it's a little bit obnoxious. So this is coffee. And then what's another flavor? What do people want?
Vanilla.
Vanilla. All right. Oh no. I forget. Oh, I did get it right. And I'm just gonna modify this slightly so that way we can do things with it. There we go. This is not vanilla, but it's what we're going to call it because I'm in charge and I get to say what we do. All right. So we have our two structures. I didn't really leave myself enough room, but we know that we're going to be redrawing these. By the way, this is similar to what you guys are doing in your practice problems, right? Yeah. Okay, cool. I don't want to be teaching you guys things that you don't need to know. Cool. So we have our two structures, and so I kind of want to let me actually double check one thing. Let me see if I can find some practice problems from your school. Oh, okay. Okay, so they want it done this way. I'm just looking at your textbook to see what your textbook is requiring. And they're pretty much happy with this. Cool. So we are going to do this, and I'm going to say we're doing it in a solution of sodium chloride. So we're doing with a sodium chloride solution. All right. First steps first, we need to identify what's the acid and what's the base, right? So we talked about how nitrogen is always a base unless if it's positive, but what other key information can we use for other problems as well? What's important to know is that acids, if we go back to that original Bronsted-Lowry kind of equilibrium, acids can be neutral or positive. And bases can be neutral or negative. So if you ever see a problem where you have a positive species and a negative species, you can be able to use that as identifying information. All right. So what I'm going to say is that the pKa of this coffee molecule is somewhere around 9, maybe slightly lower than that. And the pKa of this molecule would be about, it would be about 14. Sweet. So first questions first is which molecule is going to be the acid and which one's the base? Well, we can go to our rule about nitrogen. We can say, oh, this is the base. That's super, super simple. But what if instead I gave you something like just drawing that portion that came off? What if instead I gave you something like this? You know, and then this goes off to the benzene ring. What about in this structure clues you in that this is a base as well?
Negative charge.
Negative charge. Super simple, right? So with that information, we can say that the vanilla derivative is the base, which would make this the acid. Likewise, we can say that this becomes a conjugate base. This becomes a conjugate acid. And then what we can go from here is we can say, okay, well, we know that this nitrogen is the thing that's acting as the base. And so this is going to come over and grab that hydrogen. Does it matter which one we choose? It doesn't. They both, you guys, at this stage in the game, you don't really know the difference between the two of these. Technically, this top one would be favored, but it doesn't really matter. And so you can choose your favorite one. I'll put like a dotted line there. And so what we know based on the two structures is that we can just redraw it. I redrew it showing where that extra hydrogen is going to be. I didn't give myself enough room. Whoops, I don't know what I was doing. Ha ha ha. Don't follow me. Don't copy what I'm doing. I'm doing it wrong. Cool. So we know that that hydrogen is going away on the oxygen and it's going to have a negative charge. And we know that this nitrogen is gaining the hydrogen, so it's going to have that positive charge. And you can always check it with the math as well in case if you ever want to just double check what's going on. This is how we get our charges. Sweet. And then from here, which pKa value is the one that we're going to be moving over to the other side? Is it the one for the coffee or one for the vanilla?
Vanilla?
Going to be for vanilla, right? Because remember, pKa's can only describe acids, and this is, we're saying, is acting as the base. So this pKa must be moved over. Sweet. And then based on our third portion of our steps, we need to determine the equilibrium. And so are we going to be choosing towards the reactants or towards the product, or towards the reactants or towards the products?
The products.
Towards the products, because we're always choosing the weaker acid. And we could always double check this with our math and say 10 to the fifth is greater than 1, so this is choosing. Are we done? Nope, we are not. Because remember how I said this is an NaCl? So this really exists as Na plus and Cl minus, right? So these things aren't just going to hang around while these charged molecules are hanging around. So the final portion, the thing that you have to make sure that you're doing in your exam, is just labeling these counter charges. And just showing that the oxygen is going to conjugate with the sodium and the nitrogen is going to conjugate with the chlorine. Guarantee there will be a question on your exam where one answer will be without the ion and the other question will be with the ion. And they'll get you. Get you. All right. How do we feel about these? They're pretty straightforward, right? Once you have the steps and you kind of know what you need to do, they really become pretty repetitive. What I will say is if you have practice for acid base, try it out. Try what we worked on today. If it's not working, send me a text or send me the practice problems and we can go over them like another time and we can practice doing them, or I can record myself going through them, different stuff like that. I don't mind whatsoever. Cool. How do we feel? Good, not so good, terrible. I don't really know what we're doing. Good, cool. All right. Any questions so far on what we've been doing? No? Sweet.
So is all this stuff just on Bronsted-Lowry bases?
Say that one more time for me.
So has this like all the stuff we've done so far, is it just like relating to Bronsted-Lowry bases?
Exactly, which is the majority of what the exam will be on. They don't, in Orgo, we don't really care about the other definitions, which is nice because the other definitions kind of get a little funky. Has your teacher mentioned about Lewis or Arrhenius stuff?
Yeah, like when we went over the chapter, like we did all like kind of like went through all three definitions, but like I'm not sure which one he wants us to focus on.
Okay. If he doesn't specifically say another kind of definition, just Bronsted-Lowry. Um, all the schools that I've tutored at really only focus on it because most of the other definitions have to do with like inorganic chemistry or gen chem, which is nice because we only have one definition. Um, the the later on in the semester, at the end of semester 2, we'll talk about Lewis acids again. But other than that, primarily it'll be Bronsted-Lowry, which is nice. Just want to give you guys the PKAs that you should know. And these are the ones that over time you'll like be able to spit these out at me. Make a Quizlet, make a flashcards, whatever it takes. The faster you kind of get these in your head, the better. I'm just going to give you guys the structures. I'm not going to give you the PKAs because I'm lazy, even though I know them all. But fuck you, I do what I want. Could you imagine if I was a professor and I talked like that?
I mean, as long as you got tenure, you're fine.
That's true. I tutored at I did a guest lecture at BU and I accidentally slipped up and I talked like I normally did during these sessions and the professor gave me a look. He's like, "What was that?" It's like, "Oh, that's just how I do it." Makes chemistry more fun. Carbonic water, alcohols, phenol, amine, protonated amine.
Is the second one on the right column, is that water?
Yes, it is. It's water. So all the hydrohalic acids, hydronium ion, carboxylic acid, water, alcohols, phenol, which looks like this. It's a benzene ring with that oxygen, that hydroxy group connected to it. Um, the acidic hydrogen is that guy. Phenylamine, protonated amines, alkanes, alkenes, and alkynes. Trying to think if there's any other big ones to think of. I don't think there is. There is an amazing, amazing pKa table on mastering organic chem. I just think it's really easy to look at. So if you just type in pKa table mastering organic chem, you'll be able to find one. You really don't need an advanced one. You just need one that shows you everything. If you guys get a pKa table in your exam, that's fantastic. That's more than what the other schools get. Although when I tutored for the other professor, he didn't give their students one. So, oh well.
For Fulton, our exams are open book, open notes.
What?
Wait, they are for us?
Yeah.
Oh wait, did you say that in the beginning of class? I missed like the first 5 minutes today.
No, it's just it's in the syllabus.
Oh damn, that's nice.
What about the other professor? Is it
Maybe
like
I should double check, but I was
Alright,
also surprised when I read that.
yeah, I'll check out the syllabus then because I might have missed it the first time I read it.
wow?
I got it up right here. Let me find it. Yep, exams are open book and open note.
Damn.
I can't believe that.
It's unheard of.
Wow. These damn millennials, you don't have to study organic chem like I had to 3 years ago. I took organic chem early. I took it a year early and I fell in love with it. Orgo's my shit. Cool. Cool. All right. So we talked about the acid-base problems, which is the big thing that usually students approach me about, and they're like, "Oh, I can't do the acid-base problems. That's the only thing I need for the exam, right?" And I help them with it, and then they forget to study the acidity trends, which is actually the majority of the multiple choice portion of the exam, and it's kind of the one that is uh, big. I'm not going to give you in the past I did like the full trend thing and I went through them all and I explained it and it got really dense and I wasn't really offering anything to the conversation that you couldn't get in other resources. So what I'm going to do is I'm going to explain what the theory behind acidity stability is, because that's the thing that people struggle with. And then I'm going to show you some resources that you can go and, they'll like go through all the examples and do everything like that. And they'll do, frankly, a much better job than I have the patience for. Cool. So, acidity. I told you that to be an acid, you must donate. Okay? If you are an acid, you must donate a proton. But we have yet to talk about, well, what's a good acid versus a bad acid? What's a strong acid versus a weak acid? What makes something great versus something that's just pathetic? So before we even dive into that, I want to give you this sentence. And basically, this is the crux of everything that we're going to talk about. To increase acidity, we want to decrease the effective negative charge of the conjugate base. To increase acidity, we want to decrease the effective negative charge of the conjugate base. let's take a look at why for a second. If we go back to our Bronsted-Lowry definition, this equilibrium that we came up with, we can label in the acid and we can label in the conjugate base, right? And we know that the proton is going to be donated, and this is how we get our conjugate base, right? However, let's say that this conjugate base is really reactive. Or in other words, we're saying that this conjugate base is really strong. Then what happens is that this is going to reach right back and grab that hydrogen, right? And so essentially what we've done is we've converted our A minus right back into HA, right? So effectively there was no change. We went from HA, became A minus, but then right back, just huge arrow back into HA. So overall, there was no change. So the question is HA an acid? If it reverted right back into what it was, did it really donate?
Would it just be like a super weak acid?
Exactly. Remember, the definition of an acid is if it donates or not how well it does it. So the question of is it an acid is yes, it is of course an acid. However, it is a very weak acid. So yes, it is just a weak one. If an acid donates, but immediately accepts the proton back, it is a weak acid. That's the definition of a weak acid, is that you might donate, but your conjugate base is so much stronger that you end up converting back into your original form. Okay? And this is what we're fighting with. This is, if we want to increase acidity, we have to decrease the strength of the conjugate acid. So in order to increase acidity, we have to do it by decreasing the strength of the conjugate base. Because if you're less likely to take the proton back, it means you're more likely to just donate overall, which means you are a stronger acid. So what we're doing here is we're defining acidity in terms of the strength of the conjugate base. And by doing that, we're able to see what percentage of time does the conjugate base fail to take the proton back and thus fail to decrease acidity. Okay, so what we're essentially saying is we want to make the negative charge on the conjugate base smaller. So we make the conjugate base weaker by decreasing the negative charge. And just to double check that that makes sense, because if we're back at A minus and the minus is huge, and we have this little baby proton, it's going to want to come over and take that proton. Versus if we take a look at this other one, maybe this is coming over and it's like, I don't really want it. And then it's like, well, maybe I do. And it's like, no, I don't really want it. And then maybe, oh, I do want it. And it takes it back. So we have a much smaller, if we have a much smaller charge on that conjugate base, it's less likely to take the hydrogen back. How do we feel about this so far? Good? Kind of? Sweet. There are 5 acidity trends that we can use to describe this kind of idea of decreasing the effective charge. Okay? Do we want to go through? We might as well just go through it, just because for shits and giggles, right? Maybe you guys can look at it in your book or not. Yeah, we're having fun, right? We're doing chemistry. The first trend doesn't really have to do with anything specifically. It's kind of makes sense. Let me just make sure I'm bringing up my resource correct. The first one, and probably the most important one, is charge. Okay? The more positive the atom, the more acidic. Which, remember, saying the more positive means the less negative, right? So once again, we're talking about that same idea about decreasing the charge on the conjugate base, right? It's all the same sort of concept, all the same way around. And so very simply, it's saying that if we take a look at OH minus versus H2O versus H3O plus, that acidity goes up like that. And the pKa of this is not applicable because hydroxide does not have a hydrogen to donate. We have water, which is at a pK of 14, and then we have hydronium ion, which is at a pK of 1.7. So what I want you to notice is that by adding a proton, by making this oxygen a positive charge, we have increased acidity by, I think, 100 quadrillion times. So we have made this thing much, much, much stronger, right? Take a look at the one that we know very well, right? Here's nitrogen with a negative charge. We have an amine, and we have ammonium, or that protonated amine. Once again, this negative ammonide, I think is what it is not an acid, cannot donate a hydrogen. And amine's pK is about 38 to 35, and then this is 9.2. So again, we are increasing acidity by making it more positive, aka less negative. And once again, this is a huge, huge change. We're changing it by 10 to the 27th. So that's a massive, massive change. So the effect of a positive charge is huge. Should make sense. Pretty straightforward one, right? Cool. Second trend. Role of the atom. there's kind of two portions of this. The first portion is that acidity increases as electronegativity increases. So in other words, if we take a look at the periodic table, acidity is increasing as we go this way. And what we can do is we can compare all of our first row elements and take a look at what's going on. By the way, if I'm going too fast, please let me know. And so how does this play in, though, with our idea of decrease the negative charge, right? How does this happen? Well, remember that the other goal that we're trying to say is we're decreasing the negative charge on the conjugate base, which makes it more stable, right? So if I just write down below all the conjugate bases of these acids, electronegativity basically says that the higher your electronegativity, the more stable you are with a negative charge. So fluorine has the highest electronegativity, which makes it more able to accept the negative charge. So it's happiest with it. Fluorine is happy with a negative charge, whereas carbon would rather rip its leg off. All right? So the more electronegative the atom, the more stable it is. Okay? By contrast, the second portion of this section is that the acidity of an atom, the acidity increases as size increases. All right. So with this in mind, essentially what we're saying is that acidity increases as we go down the periodic table. And really all I want you to know for this is if I just write out a portion of the periodic table, is that as you go down in a column, you're increasing your acidity. All right. And the reason for this has to do with the fact that big atoms are able to hold on to that negative charge better than smaller atoms. So big size means more space to distribute that negative charge, and you're happier. And because you are more stable, you are a more stable conjugate base, which means we are decreasing that negative charge, which means we are increasing acidity. So let's do a little bit of practice just with this idea. And so what I want you to do is rank the acidity for the following. Let me think. Let's say we have that. We have this. Say we have that. And I don't know. Say we have that. Oh, it wouldn't be K, it would be Li. My bad. Lithium. By the way, this chemical will burn you and kill you. So be careful with it if you ever work with it in the lab. I guess I should tell you what it's called. No, I'll let it be a mystery in case if you ever come across it. If you get burned and killed by something, let me know. Cool. And I'll label these A, B, C, D. So rank them in, rank the acidity of the following. So which is going to be the most acidic and which one is going to be the least acidic? So if I have a problem like this, then what I'm looking for is I'm looking to see what's the same and what's different, okay? So the carbon chains are all the same, so I know that, okay, I'm not comparing anything on the chain length, so that's fine. So what I notice is I have oxygen, a nitrogen, and a carbon, right? These are the atoms that are kind of spelled out for me. And what I also notice is that I sometimes have countercharges, right? Sodium, lithium. And so what I know is that what this is telling me is that the oxygen here has a negative charge because this sodium must have a positive charge. And so I have a counter ion going up. Same thing here. This nitrogen must have a negative charge and the sodium must have a positive charge. Same thing here. Negative charge on the carbon, positive charge on the lithium. Oh, okay. Now I can see what I'm trying to compare. First I'm comparing charge, and then I'm comparing the role of the atom, right? By the way, people always ask me all the time, like, which is better, sodium or, not sodium, nitrogen or sulfur? You can't really compare going across. You can compare within a row and you can compare within a column, but you really can't compare going across because that's not how these two trends work. So you won't ever be asked like going across like this. It doesn't really happen because we want you to tell us one thing or the other. So taking a look at this, I know that a negative charge is less acidic than a neutral charge, which is less acidic than a positive charge, right? So I know that B is the only thing that is neutral, so B is probably going to be the most acidic. Likewise, I know that based on the role of the atom, that electronegativity increases as I go to the right? So the best, um, if I have to have a negative charge on my uh, element, on my atom, then I'm going to want a negative charge on fluorine or oxygen first. Oh, well, this oxygen has a negative charge, so it's going to be the better acid, followed by the nitrogen, followed by the carbon. Does this make sense? Kind of this approach about going at it? So you're essentially looking for differences in what's the same and what's different. And like I said, that these acidity trends are written in order of importance. Okay. So the if you're able to talk about, you know, charge and then the role of the atom, then you're pretty much golden. How do we feel about this? Good so far? Kind of straightforward, everything like that? Cool. All right. Let's go on to the next part. Has your teacher talked about resonance yet?
Yeah.
Yeah? Okay. Resonance will be a lesson in it of itself later with all of us, because it is something that I want to talk about. But it does go in these trends. So if this doesn't necessarily make sense, kind of just hold tight. We'll talk about resonance later, and I'll make sure to bring this up again. We can talk about it. So resonance is all about delocalizing electrons across pi bonds, which is kind of like saying we're trying to distribute it somewhere around double bonds. And so what I want you to know is that if we compare two alcohols, for example, here's methanol, which will kill you, don't drink it. And here's that phenol that we talked about earlier. And the question is, why is the pKa of methanol about 15 and the pKa of phenol about a million times, about a million times stronger? And I'll tell you, it has to do with how this molecule is able to push electrons around. So let's take off that proton, that nasty proton, and give ourselves the conjugate base. Because remember, all we're caring about right now is the conjugate base, because that's what's telling us what's really going on. And so what can happen is that this oxygen can bring the bond down between the ring and itself and be able to push the bond up onto another adjacent carbon. And what we see going on is that this same process can repeat itself again, and then it can repeat itself again. And if, like I said, if this doesn't incredibly make a lot of sense, that's totally fine. We're going to go over this later. But what we can say is that this negative charge can be delocalized, or in other words, it can be spread out. And so what can happen is that we have 4 locations of where this negative charge can be. It can be on the oxygen itself. It can be on this carbon. It can be on that carbon, and it can be on that carbon. So how many locations in total can we put the negative charge? 4, right? 1 for the oxygen, then 3 carbons within the ring. So what we've done is now we've turned each one of these charges into quarter negative charges. So -1/4, -1/4, -1/4. Versus what I want you to compare this with is our conjugate base of the methanol, where it has that big full negative charge, right? So it has a charge of -1 versus an effective charge of -1/4 on this oxygen. And remember, the weaker the conjugate base, the more decreased the effective charge, the weaker the conjugate base, the stronger the acid. So what we're comparing here is -1 versus -1/4. And who's the smaller negative charge? -1/4, which is why phenol is a stronger acid, because the effective charge on this oxygen is -1/4 versus the effective charge on that oxygen is -1. You have a smaller negative charge, means you're less likely to take that proton back, which means you are a stronger acid. Make sense? Cool. Cool. What I want you to be aware of is that it's not always the fact that, oh, more resonance is more better. That's not always true. If we take a look at another molecule which has fantastic resonance, is carboxylic acids, right? And carboxylic acids have a pK of 4. We look at their conjugate base. We can draw the conjugate structure. Once again, I'm kind of glossing over a couple of different things here, but that's fine. And what I want you to know is that what can happen with the carboxylic acid is that we can pull this down, push that up. And what we're essentially left with, I'm going to draw this, I'm going to draw it correctly, is now we have half charges, -1/2 charges on the oxygens. So the question is, well, why are carboxylic acids more acidic than phenol? Because we're comparing -1/2 versus -1/4, right? So shouldn't the phenol be more acidic? Why is it 10? Remember, go back to the trend that's up above. Which atom is happier with the negative charge, oxygen or carbon? Oxygen can handle the negative charge better, which is why carboxylic acids are more more acidic despite a bigger effective charge. Does that make sense?
Yeah.
Cool. That's kind of a really big concept. Again, if resonance doesn't really click at this stage, that's totally fine. We're going to have a session on it specifically, and it will be golden, and we will be all good.
It's more acidic because the oxygen is more electron.
Exactly.
Okay.
The oxygen is more electronegative, so it can handle that it can handle the technically bigger charge better.
Doesn't phenol also have an oxygen?
It does. And so the question is that we essentially have 3/4 charges on carbons versus half charges on oxygen. So which is able to just handle negative charges better anyways? Oxygen. So that's why it wins. Let's do a spot of practice because I think this is a good way just to butt in and talk about it. And then we're almost done. There's kind of one big one and then a very small one afterwards. So the practice, I don't know. Let me think. Let's say we have this guy, then we have that guy. Then we have that guy. We have this guy. And then one more. Boom. So once again, we're going to rank these in terms of acidity. And so we want the best acids overall. And so let's just talk about some things that we know right off the bat. All right. We know that oxygen is going to be better than nitrogen's, right? However, what supersedes oxygen better than nitrogen is charge, right? So do we think it's going to be B is better than A, which is better than the rest of them? Or do we think A is going to be better than B, which may be better than the rest of them?
Yeah.
It's going to be
Yeah.
B. Yeah, because charge, if you remember, was one of our first trends, right? And we saw that by adding a charge, you're increasing acidity by like 10 quadrillion times. All right. So by having a charge, you're making something super, super acidic. So B is going to be much more acidic than A. Well, why did I say that oxygen was going to be more acidic than nitrogen? Well, I go back to my electronegativity trend that I've memorized, and I know that based on my periodic table, CNOFSPClBrI, that oxygen is more electronegative than nitrogen, so I know that oxygen is going to be better than whatever ones come after. So that's how I know that A is most likely coming next. Then I say to myself, well, which is going to be more stable as a conjugate base? Something with resonance or something without resonance?
With resonance.
With resonance. So D is going to be a stronger acid than C. Right? Am I doing this right? Yep. And then finally, this leaves us E. Does this rationale make sense? I will give you another one that you guys can practice on your own, and then you can send it to me to double check, and I will do that for you. So the other set that I'll give you is that one. Oh, I copied the same thing. I'll change this to change that to NH2. So you guys can try that out, and then if you want, you can send me the your answer, and then I'll check it for you. And that'll be good. All right, good so far. Everything like that. I think pretty much we're doing pretty okay. The next one, and this is probably another one that students get confused about, but again, you're going to learn more about the inductive effect at the end of second semester. So we're not entirely, we don't have to worry about a good chunk of the inductive effect, but we're gonna talk about the part that makes the most sense. Okay. The inductive effect is a phenomenon produced by the slurping of electron density due to highly electronegative atoms. By the way, if you say to your professor, oh yeah, slurping, that is wrong. That is not a real definition. So don't be like, oh yeah, my tutor told me that. No, I did not. But it's a good way of describing what we're talking about. Because essentially, remember, name of the game is decreasing negative charge, right? So let's go back to this. Let's go back to, I don't know, maybe we're talking about ethanol because we're college students and we get drunk and we have a lit time. And what I want to do is I want to put some fluorines right there. I'm going to put a couple of fluorines. All right. And I'm going to take the conjugate base of each one of these compounds. And what I want you to notice is that the negative charge on this one on the left is huge compared to this one on the right is just a little tiny baby negative charge. It's just a tiny little thing. And so the question is, well, why? Why is the pKa of this thing around 15, whereas the pKa of this thing is around 12? How did the fluorines do this? Well, just to redraw this so it's a little bit bigger for myself, just so that way I can kind of take a look at things. Look at what's happening to this negative charge. Remember, which is more electronegative, fluorine or oxygen? Well, this fluorine is really an electronegative because it has electronegativity of 4 versus the oxygen of 3.4. So what's happening is that these fluorines are slurping, are stealing this electrons away from the oxygen. And so what they're doing is that they're sucking them right out of the oxygen, just really slurping them away, which is decreasing the effective negative charge. Okay? So by adding electronegative atoms, we are decreasing the total amount of negative charge that the oxygen feels. And by decreasing this negative charge, we are making the conjugate base more stable, which in turn makes the acid more acidic. Two parts to this. First part is more electron withdrawing groups, which is what a fluorine is characterized. Electron withdrawing groups equals more acidic. So, it's the difference of having 2 fluorines versus 1 fluorine, or 3 fluorines versus 2 fluorines. This kind of idea that more electron withdrawing, which is what is going on here. We're doing electron withdrawing. More electron withdrawing means smaller negative charge, which means stronger acid. And then the second part just means that closer electron withdrawing groups is more acidic. And this should make sense. The closer to the negative charge it has, the more of an effect it has. All right. How do we feel about this one? This one is pretty straightforward. Kind of makes sense. The big thing to know about the inductive effect, and the kind of general rule of thumb that I use for looking how it affects pKa's, is because adding fluorines, like all the previous trends that we've talked about so far, are pretty much just set what the pKa's are. This one is one that we're able to modify pKa's with, and so we use this a lot in like drug chemistry and stuff like that. You'll see a lot of like, have you guys ever heard of fluoroquinolones? That's what this is that we're adding fluorines onto a drug to make it more acidic, or to make it bind better. So the general rule of thumb that I use for myself, and by no means is this scientific or does this work 100% of the time, is that I decrease the pKa by 0.5 every electron withdrawing group. And honestly, this is just a way for me to be able to judge things in my head about what's going on. So that way, if I'm given, if I'm given this, if I'm giving these two compounds and they're like, oh, which one is more, what do you think the pKa's of these two groups will be? And it's like, I don't know. These are really only things that you can come up with experimentally. Like, you have to go look this up. You can't just know this off the top of your head. There's no way of calculating this. I know that alcohol by itself is somewhere around 15, and they'd say, okay, there's 5 of them, so 5 times, so it's like probably somewhere around probably around 13 and a half. Like, this is what I would say to myself. Just so that way I can be able to give something a number. And the reason for that is that, going back to this idea of these questions, that if, let's say, for instance, I gave you something that had like a fluorine right here, And you may know what an amines pKa is, but you may not know what a fluorinated amine is. So it's like, okay, well, it probably brings it down by like a half to a full pKa step. So that's kind of like how I think about it in my head. Not really scientific in any shape or form, but take it as it is. Does that kind of sort of make sense? Sweet. Last one, and then we are all done. It is the simplest one, and this is more just a fact of nature than anything specific. The last trend is orbitals. And essentially what we're talking about here is that the more S character, the more S, wow, the more S character the atom, the more acidic. So what do I mean by S character? Well, if we have an sp3 hybridized carbon versus like an sp2 hybridized carbon versus an sp hybridized carbon, so we're talking about something like, here's an alkane, here is an alkene, and here is an alkyne. For sp3, they're 25% S, 75% P. Versus sp2, it's 33 to 66%, versus for sp, it's 50-50. And what we notice is that the pKa increases as that goes up. And the reason has to do with that the carbon is more stable because of, it's kind of a combination of the inductive and the resonance trends, is that the fact that that carbon has that double bond or triple bond associated with it just makes it more stable. All in all, this is probably the one trend that comes up least, just because it's not incredibly big. But the big appreciable change is just by adding a triple bond, we increase the acidity by 10 to the 25, which is about as, it's about 100 times bigger than Avogadro's number. So we're talking about like an immensely huge number going on here. Sweet. And then the last thing I will give you is that you can remember these based on the acronym CARDIO, which is charge, the role of the atom, resonance, dipole, induction, which is the same thing as just saying the inductive effect, and then orbital. And so, like we said, that they're written in order of importance, so we can kind of talk about it that way and be able to. There are instances where just because like they are written in order of importance, but sometimes there's a little bit of exceptions to the rule. But for the most part, you can follow it. It'll be all good. And so that should be everything that you need to know about acids and base for your exam in 2 hours. So cool. Any questions, anything like that about what we went over? Anything that I can answer? Cool. If you do think of anything, just let me know. I have all this stuff memorized by this point, so even if you feel like you are like coming out of the blue with it, usually I'm able to orient myself pretty good. The big thing about Orgo is just make sure that you do it. I usually tell people 2 hours every day. Um, the class counts as towards that time though. So if you have a 2 hour class, great, you don't have to do Orgo that day. But the reason for that is the national average for organic chem is a 46%. So yeah, it's below failing. So it's important to stay up to date with this stuff. If you ever feel like you're falling behind, you're probably even more behind than you think you are, unfortunately enough. So make sure that you're reviewing material every day, you're looking at something, you're reading something, you're getting familiar with something, because you don't want to wait until it's the night before the exam and it's like, oh shit, I forgot to really understand what a chapter means. It's not enough in Orgo to memorize. You really have to understand what it's doing. And that's what separates people who do okay in Orgo and the people who do well in Orgo. Because if you guys are any of you like pre-med or anything like that? Or you are? Okay. For people so you're lucky that this stuff doesn't directly translate into what you have to know later, but for Pharm D, pharmacy is all based on chemistry. So what you learn in this course directly correlates to what you're going to learn in med chem. And if people just barely pass Orgo, it means that they're going to fail med chem. So scary, but I'd rather tell you now so that way you can start preparing for it, and you can have a lot of fun. What other pieces? Does this time usually work for everyone? This Tuesday's 4 to 6. If not, it always gets recorded, so that way if you miss it or if you're not able to come, it's there. Generally, if no one shows up, I just kind of take the block to myself, which just means that I'll figure out later like what I want to do about doing certain things. I think probably if we want to do like Thursdays, like 6 to 8 as another block, I'll put a poll into the group chat about if that works for people. If not, I'm happy to do like Saturdays, like 4 to 6 again, or Sundays 4 to 6, and we can like try to figure out what works best for everyone. Um, Again, it'll all get recorded. It'll all be fine. Um, Oh, on my Snapchat, I usually put lots of updates. Generally, those updates go for the MCPHS Orgo kids because I tutor 78 MCP kids a week. Yeah, my schedule is really fucked. Um,
So are you in Boston or somewhere else?
I'm in Boston, yeah.
Okay.
I'll show you guys what like a usual week looks like for me. Can you see that? That's my schedule every week.
Oh.
Holy shit.
Yeah. So um
Why?
It's insane. Oh my god.
it is what it is. So I tutor 5 schools. So if you look on my Snapchat and you ever see something pop up on my story, it's most likely for MCP. Stuff I'm giving to you guys specifically will just go in the group chat. More because there's just less of you. Trying to think. Check out the Google Drive. Check out the YouTube channel. They all have great stuff in there, great resources. Generally, if you're looking for something, you're like, oh my God, I wish I could find more SN&E practice. I have something like ready for you that you can just do. And then it'll be good. Fantastic. Any final questions, anything like that? No? Sweet. I will see you guys all next time. I'll set up a poll or something like that and send it out, and then we'll go with that. And it'll be, oh my god, so much fun. Yay, Orgo.
Hell yeah.
Cool. All right.
Thank you.
All right. Thank you so much.
Yeah,
Have a good
thank
night.
you. Yeah,
Yeah, no
Thank you.
problem.
thank you.